When people want incredibly accurate equations, they use a technique that involves what's called calculating the linear regression, which refers to setting up a line and looking at how far, really getting accurate in terms of how far each data point is falling from the mean. And so that's what this is. The line is actually meant to represent, something involving the mean, and in terms of how far each point really falls. So that way you're getting things that are roughly within the same range. This is an incredibly tedious process to do by hand. It wasn't even part of high school math when I went through high school. So what I use now is an online website, which is right here for you. There are several others. I find this one to be user-friendly. There certainly are others if you use it and you disagree. You also can calculate linear regression using a basic handheld statistical calculator or graphing calculators. They all have the capability of doing this. So see what you feel more comfortable with. If you like using the graphing calculator or statistical calculator, great. If you like using the online website, use that. It's great. Again, feel free if it works for you. Just bookmark this on your computer, and that way you can go back to it whenever you need it. When we write the equation of a line of best fit, it's going to look a lot like the linear equation, the slope-intercept form, with one difference. We reverse this order here, and the reason we reverse it is that the A is meant to be a starting point of the line, and then you're either going up or down. And again, if you're working with negative correlation, this plus sign here would be a minus. I put this on for you just to give you a sense of how incredibly tedious it would be to calculate it by hand. This is a sign for sum, which means you're adding up a bunch of different values. This refers to the average x and the average y. So again, this becomes an incredibly tedious process to work out by hand, but by calculators it'll take probably, it takes time to enter the information, but once you've entered the information into the calculator will probably need about a quarter of a second to give you the answer. Whenever we're working with a scatter plot, we're working with something that's called bivariate data. And you probably remember from your English studies that bi means two, and variate means variable, because we're working with the value of two variables. This would be the x value, and this would be the y value. So what I've copied for you is just a table that shows ticket sale value, and this is in billions of dollars here. This doesn't mean they're worth just $1 each, but this is billions of dollars of ticket sales over an 11-year period. When we work with data like this, we always say that the first year is year zero. That's where we're starting from. And so on your line, the y-intercept usually is going to be whatever the output value was during that year zero. So this could be years 2000 to 2011. It also could be years 2005 to 2016, which obviously hasn't happened yet. But that's the basic structure of a table like this. What we're going to do with this when we use it in a calculator is we enter the data as ordered pairs. So we would type in 0, 16. On a graphing calculator, they actually give you specific columns to enter the data in, an x column and a y column. On the online calculator I gave you, it's going to ask you to just enter it like this, and you would hit the return after each output value, and you just keep going, entering all this, and then you tell the calculator to work its magic. And this is what you get. The sample size refers to how many ordered pairs you entered into the calculator or computer. The mean, x, means the average of the input values, and so that was 5.5 because we went from 0 up to 11 by ones. The mean y is the average of the output values, and again with this we don't need this accuracy, so we would say it's roughly 24.6 as we're working with it. The intercept you can see right here, and that will be the y-intercept, and again we don't need this kind of accuracy on our graph, so we would say that the y-intercept would be roughly 16.3 if we're graphing it. Now if you notice on the graph that they did, it's actually falling below 16, but that's just how it kind of calculates out. So again, these are sort of estimates, they're rough estimates. If we look at the slope, again, it gives us an incredibly accurate slope, and we don't need anything this accurate. So we would look at it, we would, what would you think it would say? We'd call it that roughly it's about a 1.5. And so they're saying that the regression line equation is, remember, it's sort of backwards from slope-intercept. So they're giving the y-intercept first plus what the slope times the x would be. So again, if we were writing the equation, we would round this off and just say that it is equal to y point about 16.3 plus about 1.5x, because that's as accurately as we're going to be able to graph it. What I want you to see, though, on this graph is that if you look at this line, this point is pretty far away compared to the rest, so that's kind of an outlier. If you look at all these other ones, they are very, very close to this line here, which means that we should be able to pretty accurately predict anything if we wanted something in the middle. It's kind of different data here because we wouldn't have we can't say the data, how many tickets, what was the value of the tickets sold in half a year. But anyway, that's how it's going to look.